We have just closed our new funding round. So we are ramping up our pilot plant. We will have the first version of it ready next month.
We will see carbon taxes come in to further incentivize the CRHs of the world to shift over to this and reduce that green premium.
Putting it in concrete is really storing it for the long term. So studies right now say this is more than 1,000 years. And since we still need to build so much, this is what we really think is super exciting.
Many carbon removal solutions don't actually classify as permanent carbon removal.
So if you look in our lab, it's very different disciplinaries. Typically, you don't have that setup and that knowledge in a concrete manufacturer.
Hey, Steph, thank you so much for joining me today. I really appreciate it.
Thank you very much for the invitation.
So why don't we get started by introducing yourself and the work that you do at Ecolocked?
Hi, I'm Steph. I'm one of the 3 co-founders and chief commercial officer at Ecolocked. Basically at Ecolocked, I am responsible for all market-facing activities. So most importantly, that's our customers, really understanding the whole value chain of construction with the different pain points, the challenges, and all of the beliefs going on in there to make sure that we are developing actually a product that is required and really make sure that together we accelerate this change as soon as possible. So at Ecolocked, we are working on turning buildings into carbon sinks. How do we do that? We develop a CO2 negative building material. Right now it's concrete and additives. But going forward, we really want to go into all kind of different construction materials.
So turning buildings into carbon sink, such an interesting strapline. And I could dive into that and I'd love to, but why don't we maybe take a little step back away from that and talk about buildings at the minute. So we know by now that the built environment represents a huge portion of the global carbon footprint. From your perspective as a thought leader in this space, an innovator in this space, what does the scale of challenge look like for you?
It's huge. I think it's one of the hardest industries to decarbonize, but at the same time, or right because of that, actually one of the largest lever to really have an impact. I think you mentioned it's big. To put a number on that, I think 40% of the annual global emissions come from the building sector. And if we then break it down to building materials, that's 15%. And if we further break it down, just cement is 8%. And to put that in perspective, that's like a multiple of the whole aviation sector. When we talk about emissions, people's mind often goes to, oh, flying is bad, or, oh, let's reduce cars. But if we think about the really big elephant in the room, it's really the building sector.
Yeah, it's interesting you say that because on a recent episode, that point came up and the idea of the fact that we're flight shamed into not flying, getting trains. Meanwhile, the built environment has been trucking away with the huge carbon footprint. But I guess when we think about buildings, obviously there's sort of 2 different sides to it. There's the embodied carbon, so carbon that originates from the materials and the sort of the production of the building almost. And there's then the operational carbon from, so the actual running of the building. Where do you think the challenge lies?
So we are clearly on the embodied carbon side. I think operational carbon has been on the industry's mind for longer. So I would say it is further evolved already, solutions for the operational carbon, because a big part is just the electrification. And then there are solutions like increasing efficiency by smarter building management through digital solutions, for example. So it's not that we need to entirely change something that hasn't been done before, but exactly this is what we need to do on the embodied carbon side. I think if we break it down, there are 2 things what we need to do, right? We need, on the one hand, to reduce emissions, and on the other hand, we need to remove carbon from the atmosphere. So reduce emission means really creating new building materials. We release CO2 into the atmosphere. And in concrete specifically, it's really cement. That's the big problem, because on the one hand side, to turn limestone into clinker, which are 2 vital steps to getting to cement, you need to heat that limestone up really high, 1,300 degrees Celsius. So this kind of heat you don't get without a lot of energy, obviously. On the other hand, you have just this transition from limestone into clinker, that means there is a chemical process that releases CO2. So it's inherent. As long as you produce cement, you will always have this kind of emission. You can't get rid of it if you don't change the process or use other materials. And that's what makes it so tricky. And that's really the challenge we are focusing on.
Where would you say the industry is at in terms of actually producing these low carbon materials at scale? And how far from the finish line do you think we are?
I think we are still quite far away. If you think about low carbon materials, you obviously start basically at the carbon footprint, so the source, and think about, okay, where's that carbon coming from? And is there a way to get rid of it or change the way how something is done to avoid it altogether? And there are different solutions, not all of them even new. So we have the SCM, supplementary cementitious materials. You might have heard about it. It's fly ash or steel slag. So it's basically byproducts from other industrial processes like steel production. And there it would just be waste. But they actually have some properties that can be introduced into the concrete, and therefore the amount of cement can be reduced. So this is really promising. This is nothing new, and this is probably the largest scale solution out there right now, and also the cheapest, and we have like standards around it. So this is what the industry is already doing. The thing is that with that, we will never get completely to zero, because typically these materials are not strong enough binders to fully replace the cement. So we always still need cement, lower amounts, but still. Then there are startups and other innovators like universities, etc., working on alternative binders, so completely getting rid of cement or changing the way how cement is produced. I talked earlier about the high temperatures and this chemical process that releases the CO2. So if you think about electrification there, for example, as well, there are ways of how people currently try to still get to cement as a binder, but without the negative byproducts. Then there are completely different ways when we think about, for example, capturing carbon, mineralizing it, and then introducing that into the system, or using captured carbon and bring it into the mixing of the concrete, thereby hoping that the concrete kind of encloses the CO2. That's recarbonization or carbon curing. There are digital solutions, again, ways of how to do mix design optimization to get to the minimum possible level of kind of clinker or cement, while still keeping the mechanical properties that are required. And yeah, then there's us, where we are basically trying to introduce a CO2 negative material that also has some functional benefits for the concrete.
And then some of those sort of later examples that you gave there, particularly getting into the world of biochar, that is unlocking the idea of a carbon sink, right? Going back to your original point around turning buildings into the largest man-made carbon sink. I'd love to dive into that. What's your vision there? And what sort of role do some of those low carbon material innovations play in unlocking that idea of a large carbon sink?
Yeah. And maybe if we start by what is a carbon sink and why do we need it? So obviously CO2 has been around and carbon in the atmosphere for millions of years. And there's this natural carbon cycle that we, humanity, brought out of balance when we started to extracting all of that oil and that gas. But carbon sinks are nothing new, and they are very natural. It's like trees store carbon, obviously, and also the sea stores a lot of carbon. Then there are like moors. There's so much out there that stores naturally carbon. But now we obviously need to do more, because we released more carbon that has been like locked in underground for millions of years. And we need to do that again. Basically, if you heard the IPCC, they said we will not reach our climate goals by just doing carbon emissions, unfortunately, because we are too slow and there are still areas where we can't fully decarbonize. Plus, we've pumped so much CO2 into the atmosphere. So we also need to remove carbon from the atmosphere, additionally to bringing down all the emissions. And the question is then, A, how do we store them? Where do we lock this carbon in? And B, how do we finance that? because generally carbon removal is extremely expensive. It's very new technologies. If we think about direct air capture or mineralization, for example, it's very emerging technologies. They are not scalable yet, and they need a ton of electricity and energy. And we know that we have like renewable energy, that's great, but we know also that by far this is not enough for the level of energy we would need here. So I think for a very long time, this will be not a solution that can have an impact at scale. And it will probably for a long time also just be for the richer nations who can afford this very capex intense and energy intense solution. But once we have that carbon, again, it needs to go somewhere. And a lot of people right now either think about pushing it like below sea level or in extracted oil fields. And the question is always, okay, and who finances that? And how safely stored is there? How permanent will it be locked in there? And something that science is currently really excited about is, and we can talk about that later, why they are so excited about it. But then also, once we have this biochar, where can we store it? It's a material, it's a solid material. It doesn't make sense to put it somewhere where it's not really safe. So biochar can be put in soil. The Mayas actually did that many thousand years ago, and it can still be found there. So that's pretty remarkable and means, yes, carbon can be actually stored quite long. But we also know this is not always the case. Depending on temperature and bacteria activity and other things, the carbon is probably released between 50 to 100 years. Putting it in concrete is really storing it for the long term. So studies right now say this is more than 1,000 years. And since we still need to build so much, this is what we really think is super exciting. So we have something here that is a carbon sink that is still growing. It has functional benefits, therefore people are willing to pay for it, so we can also finance this. And that's something that people often forget. Plus, it's safe.
And 1,000 years is incredible because that very much counts as permanent storage. So I think something that would shock a lot of people is that many of the carbon removal solutions that we see spoken about quite highly at the minute don't actually classify as permanent carbon removal because it can't guarantee the storage for hundreds and hundreds of years. So 1,000 years is really quite breathtaking. I want to just be sure that everyone listening and watching is completely aware and comfortable with the idea of biochar. Steph, would you mind just maybe explaining what it is that we mean when we refer to biochar?
Yeah, sure. Biochar is made from residue biogenic materials. If you think about waste from the forestry, from agriculture, from the food processing industry, or also think like manure or sewage sludge. All of this is generally considered to be waste. It's biogenic, thereby it has carbon stored by the plants, for example, through the photosynthesis. And typically, at the end of its lifetime, it would decay and thereby release the carbon back into the atmosphere. What happens when we do biochar manufacturing is the material is heated under the exclusion of oxygen. And thereby we create a very kind of stable material that has solid carbon included. So depending on the kind of feedstock that is used and the pyrolysis technology, there are different ones, you can save up to 3 gigatons of CO2 on 1 ton of biochar.
And so that removal, that sort of avoidance of CO2 is that prevention of the future CO2 being released, or is it actually the absorption of new CO2 into that organic matter?
That's a good question. It's the prevention of the release. If you would let the material decay, CO2 would be released depending on where that material is within 2 years or 50 years or maybe 100 years. And with the biochar, you prolong that process of it being locked in somewhere.
What does the process look like to turn this quite an incredible material, this sort of organic material, into a material that can be used to prop up buildings? What does that transformation journey look like?
Yeah. So I would say the challenge here is that the material is incredibly diverse. So if you think about all of the different feedstocks I just mentioned and the different pyrolysis technologies, we have a material that is extremely different in terms of its chemical and physical properties. So biochar is not biochar by any means. Like every biochar is very different to one another. And that's the difficulty, because if you want to introduce it in like end product like concrete, we need to have a very stable, consistent, and high quality material. Especially biogenic materials are really like problematic because they tend to deteriorate the quality of the concrete. And what is more important than the stability for buildings or bridges or anything, we need to make sure that the quality is like not touched in any way.
If you're taking organic matter from the environment, you cannot rely on the consistency. This is something that came up in a previous conversation, looking at what we can do with wastewater sewage.
Mm-hmm.
The one of the challenges with the wastewater treatment industry is you can predict a decent proportion of what will enter a treatment center facility because of population, because of local demographic elements, and various other factors. But you can't guarantee everything that will enter. You might get shopping trolleys, you might get packets of crisps or whatever else, and various others,
Mm-hmm.
quite a spectrum. But you can't guarantee it. So actually relying on the steady flow of that organic matter, I imagine, is quite a tricky challenge for the biochar sector. But it did sound as though you had overcome this challenge around inconsistencies. What's your sort of approach to it?
I would say we are in the process and working towards overcoming it. Yeah, so basically, we decided that we don't want to produce biochar ourselves, because if you really want to cater to the construction sector, you need huge quantities. Otherwise, you will never be relevant. It's one of the first questions they ask, like, how much volume can you deliver? And there are people who produce biochar and they do it well and they're experts there. Our approach is really helping this industry that is producing the biochar and that is contributing so much to carbon removal to find a scalable and economically attractive end application. And this is, in our opinion, the building sector. And doing this translation of here we have highly volatile materials and here we need something very consistent, we are the bridge between that, right? Like we take all of these different materials, we have kind of product development and optimization platform. It's lots of analysis, lots of data in there that really helps understanding what are the properties chemically, physically, what are then the performance indicators for the end product, and how do we need to select them and further refine them to have then the optimal quality for the construction sector.
Would you mind giving a couple of examples of how what these sort of variations in the process look like in terms of that sort of demand side and the supply side?
When we talk to our customers, which are at this point concrete manufacturers, they typically have one concrete that they need, right? And where they are looking for material to decarbonize it or to reduce the net footprint in our case. And we will get the requirements for that product and we will get the concrete recipe. And with that, we basically start looking at what is the current carbon footprint. And then we understand how much biochar or how much Ecolocked materials is required to get the reduction that the customer is looking for. And is that possible within the boundaries they have defined? So typically you have requirements with regards to the workability. The concrete needs to, in its wet form, needs to be flowable, needs to harden at a certain rate. There are certain requirements for kind of while the concrete is still wet, so people can actually work with it. And then when it has completely dried out, when it's cured, there are requirements with regards to the strength, for example, or the durability, or the ability to resist freeze or thaw, or these types of things. So knowing all of these requirements and the original recipe, we can then basically determine what Ecolocked material is required to remain or keep all of the other things true while reducing the net footprint. And based on that, we can then look at the input side.
That will then determine the type of feedstock that produces the biochar. Is that right?
So basically, yes, we don't always start from scratch. We have certain biochar families, as we call them, which have basically pretty similar characteristics. And out of that, we know then this biochar family is a particularly well fit for that type of end application, because you obviously also want to think about proximity, right? Longer term, what we do not want is that the perfect biochar for construction product in or project in London is in Kuala Lumpur. And then you have to have huge, let's say, transportation emissions because you transport it across the world. We really want to make sure, since waste is everywhere and construction is happening everywhere, to have this hyper local approach where we look what are local waste streams and ideally match them then to the construction project.
I imagine the research and the groundwork required in order to be able to actually replace traditional materials with biochar could be quite tiresome and lengthy and costly for large building manufacturers. So actually you being able to plug that gap and join the dots, I imagine is a really valuable service for companies.
Yeah, no, that's true. Interestingly, a lot of companies that we talk to have at some point tested with biochar and then stopped because they just couldn't get good results. And that's, I think, the main reason why we are needed, right? Because it's two completely different worlds, and so far they don't talk to each other. So if you look in our lab, we have environmental scientists, we have material scientists, we have chemists, we have concrete technologists, we have civil engineers. So it's very different disciplinaries that need to talk to each other to make that translation. And typically you don't have that setup and that knowledge in a concrete manufacturer. And so you can't just take any biochar and put it in any concrete product. It's really a lot of science in there, and that's what we perform.
And what tend to be the sort of the key outcomes of actually shifting proportions of the building materials to biochar?
I would say the biggest benefit, of course, is to reduce the net carbon footprint by storing carbon in the product. So this is insetting, and obviously this should not come alone, right? Ideally, we reduce the emissions, and then this insetting comes on top. Meaning, ideally, we still get rid of the cement. Ideally, we still ramp up the number of SCMs in there, or find other solutions to really get the footprint already to zero. But typically, these technologies either are not scalable yet, or in the case of SCMs, since we change the way how steel is produced, there soon will not be enough steel slag available, for example. Some of the kind of tested materials are falling away. And a lot of the new technologies will require a lot of capex. What biochar can really be is the bridge until we get to this reduction of emissions. Already now, we can bring the footprint down, and it's in a way that is very simple for our customers to integrate. They don't need new infrastructure. They don't need to change their processes because we are just delivering an aggregate or an additive that can be included in the mix the way how they always produced.
So they really notice no difference, really. And is the impact on, say, the civils, the structural elements, pretty consistent with traditional?
So that's a requirement, right? So you have certain requirements with regards to durability, strength, etc. And we need to be able to prove that our material doesn't negatively affect them. If at all, we can enhance them, of course, because no one is unhappy about an even stronger concrete. But that's always the kind of minimum threshold, that we don't negatively affect any of the other properties. And we can even enhance some functionalities. For example, with biochar, we can increase insulation, which is huge if you think about like energy efficiency requirements for buildings, the less like heating and AC that you need, but also, for example, less insulation materials and therefore more space because the walls can become thinner. So this, for example, is a big effect. Also, if we manage, and we know we can do that, the durability of material, so that you don't have to replace, for example, paving stone after 80 years, but only after 200 years. That's a lot of like waste and emissions also that you save. So there are also a lot of secondary benefits additionally to the CO2 footprint.
So I guess us on the application side, it sounds as though it's this incredible material that needs to be used widespread. Do we have enough feedstock available to be able to really support the potential demand that we could see in the future?
Yeah, the short answer is yes. The longer answer is right now we have 3 gigaton of unused waste material every year on this earth. So there is a lot of potential. I think in former times, people often thought about biochar just made from wood. And there's not too much wood around here, and we can use wood for other purposes as well. So it's always this, oh, but is there enough? But there's so much more, even from agriculture, rice husk, cacao shells. There's so much, and it's being produced all over because we need just food, and this is a byproduct of that, and this is not used mostly. So there is a lot of potential for growth still.
And is on the processing side, are there any sort of like evolutions or real transformational shifts required in order to be able to sort of process this scale of organic material into biochar that the industry needs?
So there have been a lot of progress over the last couple of years. And I'm by no means a pyrolysis expert, but I know that a couple of years ago, people focused on the wood-based biochar for a reason, because it was like the easiest to process. And at this point, there are great companies out there who managed, for example, to produce biochar feedstock that is very moist. That was not possible earlier. So there has been a lot of progress also in terms of scalability, moving from modular to continuous production, these types of things. I think it will not stop. I think there will be continue to be progress, but we can also, for example, see in prices have dropped by so much, even just in the last 2 years, at a much faster rate anyone would have expected. And I think that's always a good indicator on where this industry is towards scale.
And on the price points, would for example, a CRH be incentivized to use biochar in their materials, or is the economic incentive still on the sort of the traditional building materials makeup?
It's still the traditional material, unfortunately, is still a lot cheaper. We are talking here about things like limestone and sand, right? They are incredibly cheap. I think we have a lot of externalities here that should be priced. I think there was a lot of coverage in the media around the negative impact or extracting too much sand and therefore drying riverbeds or riverbeds that have no flow more, destroying biosystems. But this is not priced in. Yes, we have a green premium still. We are currently looking in some products where we are pretty sure we will be price competitive even in the next 1, 2, 3 years. But I think we should also not compare our Ecolocked aggregates or additives with the materials they replace, but we should compare it with other decarbonization technologies. And there, obviously, this is a really cheap solution.
If you look at some of the cost jobs, point towards capture and other technologies, other removal technologies, I imagine on the materials side, using an organic matter which is freely available to us, was relatively freely available to us at scale, I imagine that the cost differential is quite significant. But also, I hope that we will see carbon taxes come into place where there will be taxes levied on building materials that don't contain any form of those low carbon components. So I hope that will then further incentivize the CRHs of the world to shift over to this and reduce that green premium. One last question to finish. What does the next year look like for you?
We have just closed our newest funding round, which means we have now new fresh money to invest, to throw at the problem and to further accelerate. And so we are ramping up our pilot plant. We will have a first version of it ready next month already, and then looking to scale that up. And we have a lot of ongoing trials with customers. Our first product, ELM0, is already in the market. So there's also a question about scaling that up. and also looking into new product lines.
Amazing. Congrats on the funding round. That's super exciting. Steph, thank you so much for your time. I really appreciate it. I'll see you soon.
Thanks for the conversation.